Okay, let's look at expectation of a function of a random variable. So we're going to let x equal a random variable with probability distribution f of x, and then g of x is the function of the random variable x. So the expected value of the random variable g of x, so that would be, if it's discrete, let's look at discrete first. It's mu g of x is equal to the expected value of g of x is equal to, it's discrete, so we do summation of all the x, g of x times f of x. And for continuous, the mu, or the mean expected value of g of x, is equal to the integration. With continuous, we integrate from minus infinity to infinity of g of x times f of x. Okay, let's look at this discrete example. So we have, suppose the number of cars x that pass through a car wash between 4 and 5 p.m. on any sunny Friday has the following probability distribution. So number of cars through the car wash from 4 to 5 p.m. We could have 4 cars through, 5, 6, 7, 8, 9. And the probability of each of those, so the probability of 4 is 1/12, 5 is 1/12, 6 is 1/4, 7 1/4, 8 and 9 are 1/6. So we have a function, g of x. So g of x is equal to 2 times x, the number of cars that went through the car wash between 4 and 5, minus 1, represent the amount of money in dollars paid to the attendants. So we want to find the attendant's expected earnings for this particular time period. So his pay is dependent on the number of cars that go through the car wash, and we're going to look at how much did he get paid for this time period, 4 to 5 p.m. on a Friday. So let's go ahead and let's walk through it together. So we have the expected value of g of x, and this is discrete, so we're going to sum, is equal to the expected value of g of x is 2x minus 1. So 2 times x minus 1 is equal to the sum as little x goes from 4 to 9 of 2 times x minus 1 times f of x. So we would take each value of x, so we would take 4, so 2 times 4 minus 1 times that probability that the number of cars is 4 is 1/12. Then we're going to add to it 2 times 5 minus 1 times 1/12. And we're going to do this for each of the values of x. So 2 times 6 minus 1 times 1/4 plus 2 times 7 minus 1. So when we do this math, we find that the expected value would be $12.67. So we could see that sometimes x is a function. So g of x is a function of x times f of x. Okay, let's look at joint probability functions and their expected values. Let big X and big Y be the random variables. And with joint probability distribution, f of xy, and the mean or expected value of the random variable g of big X, big Y is, so let's look at it for discrete. We have mu of g xy is equal to the expected value of g of xy. And for discrete, it's summation, so we'd have the double sums. So we would have the sums of the x's and the sums of the y's of g of xy times f of xy. And then for continuous, we would have integration. So we would have mu of xy is equal to the expected value of g of xy is equal to the integration from minus infinity to infinity of both x and y for g of xy f of xy dx dy. Okay, let's look at this example. This is a discrete example. We're going to let big X and big Y be the random variables with a joint probability distribution indicated in the table. So we have the table here on the right. We want to find the expected value of g of xy, and we know that g of xy is equal to x times y. So we're going to find the expected value of xy. So when we look at the x's, x can be 0, 1, 2. Y can be 0, 1, 2. When x is 0 and y is 0, xy is 3/28. When x is 1 and y is 1, 3/14. When x is 2 and y is 2, it's 0. So you can do this for every combination. If x is 2 and y is 0, 3/28. So those are the probabilities when of the specific values of x and y together. So we want to do this solution. So we're going to do our double summation as x goes from 0 to 2 and y goes from 0 to 2 of x times y times f of xy. So if we walk through each combination, we have 0 for x times 0 for y times 3/28. So that would be this point, 0, 0, 3/28. And then if we have x is 0, so we're going to add to it, x is 0 plus times y 1 times x is 0, y is 1 times 3/14. And then we do x is 0, y is 2, that's 1/28. So x is 0, y is 2, that's times 1/28. So we go on, x is 1 times y is 0, that's 3/14. And then we'll come over here, continuing on, x is 1, y is 1, that's 3/14, plus x is 1, y is 2, that's 0. Okay, so what you can see is that most of these are multiplied by 0, so they zero out. In fact, only one of them is not multiplied by a 0, and so the expected value for this function would be 1 times 1 times 3/14. But that is how you calculate. Now, this g of xy equal x times y, if that was x plus y, we would be doing 0 plus 0 times 3/28. So depending what the function is, it is not always a multiplication. Depending what the function is, that is what you multiply by the probability distribution. Okay, so let's look at this continuous example. So we want to find the expected value of g of xy when that equals big Y divided by x. So our f of xy is equal to x times 1 plus 3y squared over 4 when x is between 0 and 2 and y is between 0 and 1 and it's 0 everywhere else. So the expected value of g of xy is equal to the expected value of big Y divided by x is equal to, so we're going to do our double integration. So we're going to go for y is from 0 to 1, and for x is 0 to 2. So we're going to multiply y over x times x times 1 plus 3y squared divided by 4 dx dy. So the first thing we'll do is we'll do a little simplification, so these are going to cancel. So now we're going to have y times 1 plus 3y squared divided by 4, and when we do our integration, this simplifies to 5/8. So the expected value would be 5/8.